All right, good day, everybody, and welcome once more to Historic Flight Foundation's Winter Lecture Series. This is a repeat of a talk that we gave in, I think, January of 2007. No, right there, January of 2017. And this time we're going to talk about the engines that were developed for the purpose of the races in the golden age of aviation in the 20s and 30s. Now, I think as all of you know, the span of focus for Historic Flight Foundation is really 1927 to 1957. But in this case, in describing the engines that supported that time period, we're going to have to stretch that starting point back to right after the First World War, because many of the design development items and the innovations that were made in the engines that went into these racing airplanes, a lot of that occurred during that time period just prior to 1927. So given your indulgence on that, we'll kind of press into it. Right after the First World War, many successful businessmen, and in this case, primarily newspaper owners, wanted to retain and then expand their circulation. And many of them became sponsors of various races. And that was pretty well throughout the world too, in Europe as well as in the United States. And I've called this thing here the heart of a racer, its engine. And really, I think, and maybe I'm biased on this one, but the engine to me is the heart of an airplane. In this particular case, we look at the various ideas that were put about to support these racing airplanes. So now, wait a moment, I need to, there we go. Okay, this is one idea of a racing airplane for a gentleman. And with all of these airplanes, it has an engine, it has a propeller, and it has an exhaust system. The main components of any major propelling device. This particular thing was done by an artist in Europe, and he built this thing full size, working. Obviously, it didn't fly, but it did move, and it was exhibited throughout the 40s or the 50s and 60s, certainly. However, it does make the point. And what I'd like to do is to, first of all, look at some fundamentals about the kind of thing that came together for this race era, and to look at some trends, and then to, after we do some basic understanding, look at some trends, and then get into how these things came about. First thing, of course, was the businessmen who wanted to support efforts to keep their circulation in the case of the newspaper owners. They were looking at events that they could put on for the public. And therefore, most of the racing airplanes were what I'll call point design, which meant they were very fast for the spectacle that went with that. And they were all at sea level or very close to sea level, and both on land and on water. And of course, the first thing the engine designers had to worry about was really creating power. And this particular chart here just shows a four-stroke engine and some of the factors that affect the power. Now, all of the engines we're going to talk about today are going to be operating on the Otto cycle or the four-stroke cycle. When you look in the textbook, that will tell you that that is induction and compression and power and exhaust, 4 strokes. When you first get into it, the easy way to remember it, of course the media loves this one, is suck, squeeze, bang, blow. Personally, I prefer Stanley Hooker's definition, which is 1 stroke for power and 3 to wear the engine out. However, the power generated here is a function of the amount of air and fuel that you can pump through that engine at a given time, the volume of the cylinder itself, the fuel type, which is the heating value of the fuel, the calorific value, the octane rating, which we'll talk about as we get into this thing, is a measure of the degree of compression that the fuel-air mixture can stand before it starts doing funny things with the combustion process. The fuel-air ratio, because there is a span of ratios of fuel and air between fully rich and fully weak, which will support combustion. We talk about the air density and the pressure involved here, and with a racing airplane, obviously that's sea level pressure and sea level air density, with a real application later on in the military or a commercial field. That will obviously be a function of altitude and speed and the like. We'll talk about the combustion efficiency, which is just what it says, how efficient the combustion process is. And important with a piston engine and a jet engine for that matter, what the dwell time is, so-called, of that fuel-air mixture while it's burning inside the engine. And one tried to design an engine that had sufficient dwell time there that you could complete the combustion, or the complete combustion of the fuel in the air inside the engine. If it went out through the exhaust, it went out either as heavy hydrocarbons, soot, or smoke. And of course, many of the early engines have a lot of that exhibited. And the other thing to recognize here in generating power is that there's a lot of heat lost. We'll talk in a second with the next chart about the combustion process itself, but only about 35% of the energy, chemical energy involved in the fuel that's used is actually used in generating power inside the engine. The rest of that energy is lost in terms of heating up the engine itself and wasting energy through the exhaust. This became very important later on when it got around to exhaust superchargers, which we'll briefly mention right at the end of this exercise. But there we go, that's kind of the fundamentals of how the engine operates to generate power. But the purpose of generating power is really to create thrust that will move an airplane through the atmosphere. And this chart shows the process of taking the fuel in the air, and recognize that the hydrocarbon fuel won't burn by itself. It needs to be vaporized with air, and that fuel-air mixture will now burn. So we go through a combustion process converting the chemical heat in the fuel and the air to heat energy, or the chemical energy into heat energy. That heat energy is applied to the pistons within an engine, and through a series of cranks produces mechanical energy. And that mechanical energy is typically how we will measure the power of an engine. But that's not much use to an airplane until we convert that into propulsive energy. And in the same way that the fuel-air process and the combustion doesn't recognize all of the heat that's available from the chemical energy in the fuel, each of those conversion processes operate at an efficiency of less than 100%. And like I said, the combustion process is probably the biggest loss process going. However, all those other conversions also have a price to pay. And of course, in creating the maximum power, you want to minimize the amount of wasted energy that was going. So, okay, given that, let's take a look at some trends. Now, I've got a couple of charts here that are taken from a book called Race with the Wind, which is describing the history of the many of the racing airplanes that were used during the 20s and 30s. And this is one of the charts that's included in there, which shows that back here in 1920, which is where this chart starts from, racing airplanes were probably flying at a speed of roughly 90 miles an hour, faster than the fighter airplanes of the day, right after World War I in the case of 1920. And although this chart here shows a straight line, which characterizes the racing engines, it normalizes the data that's available on that chart. However, the time it takes to get from an airplane or an engine that will operate an airplane at 200 miles an hour to operating in a fighter airplane in a practical military environment took, in this case, between 1920 and 1930 to recognize. So in other words, the application of technology that was in the racing airplane into a practical military airplane proceeded at the speed of metallurgical development and manufacturing development, really. And that took a long time back in 1920, during that period. If we go to the top end of this curve, we see some other data which describes racing airplanes. And the line that's dotted up there shows a divergence between these two lines. I'm not sure how to interpret that, because when we really look at the advance in technology, I would have expected those lines to converge, not to diverge. But not to worry, we'll press on from there to take a look at what happened a little later. The Thompson Trophy airplanes, and the Thompson Trophy was a trophy that was all part of the national racing calendar, but this is up beyond the end of the 1920s, and the Thompson Trophy race was primarily a short circuit pylon race, which nevertheless involved some high technology racing airplanes, but in this case, we're only looking at a difference in speed of roughly 40 miles per hour between military airplanes and the Thompson Trophy winners, and the time between getting the same airspeed out of the military airplanes compared to the racing airplanes took something like about 4 years. So this, I think, recognizes the fact that by the time we get into the 1930s, metallurgical research and manufacturing processes have advanced sufficiently that it took less time to exercise the technology that was developed in the racing airplane. However, the point is that it takes time, and you are looking really at all of these racing airplanes as being point design, near sea level, and as high a speed as we can possibly squeeze out of it. Now let's look at some trends here after World War I, between the wars really. And here I must give a vote of thanks to Liz Matzella, who is the IT manager who's looking after all of these presentations here, and is the reason that you can see this data and see my ugly mug on the screen. Liz put this together for me 3 years ago when we did this thing originally, and it's all based on airplane piston engine performance that's defined in a book by Herschel Smith that covers pretty well every airplane engine between the wars. What you see here is first of all, an orange line up the top there, which is a trend line in inline engines. Now, at the end of World War I, as the large rotary engines that were common in most of the airplanes in World War I began to top out at 220 odd horsepower or thereabouts, we see a line that describes inline engines which were liquid cooled. And obviously the rotary engine created its own air cooling because the cylinders rotated with the propeller. But at the end of that time period, inline engines became more prevalent because they were a more efficient cooling process. And what we began to realize, particularly throughout the engine design process, and this goes for jets as well as piston engines, is that the problem is not so much the ability to develop power, it's cooling the brute that's the real technical challenge. And we'll see how those challenges were addressed during the development time period we're talking about here. What you will see is some points, orange diamonds that are in there, which showed that back in about 1917 or thereabouts, we had some outstanding engines that produced higher power than their local other engines that were prevalent at the time. The reason is that, again, these are point designed. They don't have to be durable, and therefore you can wear them out real quickly. And in terms of the airplanes that were set up there in 1924, you'll see two points out there where I'll see if I can do this with a point. These engines right here, these are developments of the Liberty engine that we'll talk about in a minute. And then one major outstanding one is this one up here, which is the Schneider Trophy engine that was produced in 1929 for the British entries, the Supermarine entries to the Schneider Trophy races. And the reason that's so high is that at the time, Rolls-Royce decided to throw everything to the wind here and over-supercharge the engine at sea level, which made it a very short duration engine, but gave it tremendous amount of power. We see here the trend line of that orange line there, slightly ahead of the trend line for the early radials, the green line that's under there. Now, the early radials that we'll get into talking about in a moment had a disadvantage in as much as you got to consider that in an engine burning hydrocarbon fuel or gasoline, if you like, it takes the oxygen in 15 pounds of air to burn 1 pound of fuel. And so the problem with the design of the engine isn't so much getting the fuel into the engine, it's getting the air in and the exhaust gases out. And the inline engines had an advantage there over the air-cooled engines in that it was possible to put a double set of valves into a cylinder. And it's not so easy to do that with a radial engine. However, by the time we got to 1929, which is where the blue line here and the green line intersect, radial engines were better understood and they allowed further development of the compression in those engines. And that was also the start of the ability of an engine to be supercharged, and that allowed all of those blue points to take off literally like rockets with later years getting up towards World War II. But we'll talk about that as we go through here. So, okay, that's horsepower development. Let's take a look at the next chart, which is just a similar chart of horsepower per cubic inch. In other words, how much can I get out of a given capacity of airplanes? And that had a lot to do with the way you grow an engine. Likewise, power to weight ratio shows a distinct advantage here for the inline engine. Now, you'd think an inline engine with a water cooling system would be a lot heavier than a radial engine. And in terms of the dry capability of the engines, that's not far off right. But in order to create a high horsepower per pound ratio, you need to run an engine at high RPM. Having said that, one of the inline engine advantages was that you could put a double set of valves in a cylinder. With a radial engine, you couldn't do that quite as easily. And so if you only had 2 valves in the cylinder, you had to make them bigger valves and you had to make them open further to absorb the capacity. or the air fuel charge that was pushing through the engine. And when you ran that at very high speed, you had more valve inertia there, which created something called valve bounce. And it also meant that you had to allow a fair amount of space there to open those valves before they hit the piston. And that was the disadvantage for the air-cooled engine. So there was a very distinct advantage there then for the inline engines. Now, in other words, here's just a summary of it, if you like. And there's one more point I want to raise in this chart. During World War I, several inline water-cooled engines were prevalent. Hispano-Suiza being one of the major ones, a V8. The Hall-Scott engines that we'll talk about in a second, the Packard engine, the Liberty, and the Curtiss inline engines created by Glenn Curtiss, of course. And one of the things all of these designers ran into immediately was a thing called the square cube law, where the heat generated by burning the fuel in a cylinder was proportional to the cubic power of the cylinder dimension, the bore, if you like, or the stroke, the matter which you use. And what that amounted to also was a recognition that the amount of surface area that was available for either water cooling or later on for air cooling was a function of the square of that same dimension. So as you get bigger in terms of capacity of the engine or the capacity of a cylinder, it's less efficient or less space available to cool the engine. So the way to increase capacity of the engine and therefore power was to have more cylinders than to have bigger cylinders. And we'll get into that one as we go through to see some of the development. Also, the liquid-cooled engine had 4 valves per cylinder typically, and that improved the characteristic that I mentioned a minute ago, the breathing, the ability to get the air in and the gases out. As the RPM increased, it was necessary to change the timing of where the spark plug initiated combustion. And so advanced retard ignition requirement was necessary as you played games with the RPM increases. The use of aluminum was extensively researched, and aluminum became the preferred material for really looking at all of the structure of the engine, other than the liners for the cylinders, because of where those were typically steel. And then the other thing was that those cylinder, those cylinder liners were typically screwed into the cylinder heads and the barrels because that was a more efficient sealing process than using gaskets and bolts. And that became quite prevalent later on when we get to some of the liquid-cooled engines. So the air-cooled engine really was superseded by the liquid-cooled engine as the preferred way of going immediately after World War I. So let's take a look at a couple of people involved in that. And here are 2 of them. Hall-Scott was a well-known company that designed engines for all sorts of applications. And you see one of their straight 4-cylinder engines here with an overhead camshaft and overhead valves, which of course meant the engine was a lot lighter. The Elbert Hall, who was the engineer of the company, did a lot of research into the shape of the combustion chamber to make the combustion more efficient. Pioneered really the extensive use of aluminum here. And the key to the whole thing was that these engines had parts that were interchangeable, a characteristic of, I must say, the American industry, as opposed to the European industries that took pride in more hand-built engines, if you like. And it was Albert Hall, who worked with Jesse Vincent, this next man. Jesse Vincent was a He was the chief engineer of Packard for many years. And it was Jesse Vincent who, he was a self-educated guy, really, through, he educated himself in the engineering world through all sorts of communications and really postal systems, communication media that was used to educate in those days. He came across, or came upon, his natural instinct for engineering quite because of his breeding. His father was the chief engineer of the Union Railroad system during the American Civil War. And a lot of that, I think it was Jesse Vincent created his first engineering application by sharpening tools and got in as a very young kid, really as still as a young student who got stuck into replacing and servicing various tools for lathes and chisels and this kind of thing early on in life. And so he came across his engineering education quite early. He also got into the habit, working for the Packard company, of exercising a lot of his ideas in racing cars before he put them into aircraft engines. But his real claim to fame early on, when it came to the period immediately or during World War I and immediately afterwards, was in developing this engine, the Liberty engine. When the United States got involved in World War I in April of 1917, Woodrow Wilson made some very ambitious targets for applying the ability of American industry to producing power plants for the war effort in World War I. And he designated Jesse Vincent as the guy that he would like to head up the team to develop power plants for First World War application. Jesse Vincent immediately got a hold of Bert Hall from Scott Hall, and the two of them put their heads together. And they said, look, there's a lot of engines available worldwide that we could use. However, I think we should take a look at best practices of all the engines that we know about in the world. We should plagiarize unmercifully, which they did, ideas from all of these engines and put together our thoughts on a new engine. Within 6 weeks of the assignment from Woodrow Wilson, they put together an operational L8 engine, a V8, 45-degree V8 engine. And it was Jack Pershing, General Jack Pershing, who commanded the United States forces during World War I, who came along to him and said, guys, I need more power than that, make it a V12. They did just that, and this was the result. A nominally 400 horsepower engine that was used in many, many applications on the ground and in the air during the American involvement with World War I, and immediately afterwards, of course, because these engines came along very late for the overall context of World War I. And you see the characteristics here of that engine. Nominally 400 horsepower, 5-inch bore, 7-inch stroke, and the engine looks like a piece of active machinery. Here's the development of that engine. After World War I, a lot of the original racing venues got started up again. And one of those was the Pulitzer race, which involved, really this was kind of the start of the national air races after World War I. And in the case of the 1920 Pulitzer race, the airplane that's up there in the top picture is a Verville Placard R1, designed by a little airplane company called Verville, which operated out of Detroit, and it used a Packard engine. And it was a development of the Liberty engine, which is shown in that left-hand picture there, which is a 638 horsepower version, which was a development of the Liberty. I said the Liberty was about a 400 horsepower engine, and this was just a little bit of a growth to that, and was one of those early standout engines, the 1A2500, which appeared in those early trend charts. This allowed that Verville Placard airplane to fly at 178 miles an hour during that 1920 Pulitzer race. And it was flown by an Army lieutenant shown on the right, called this Mosley. Mosley not only was a very active Army officer, he was also later on a vice president of Curtiss-Wright, looking after a lot of the airport activity that went along with Curtiss-Wright. He was the vice president of that company. And he was also quite active in the start of US airlines on the West Coast, particularly of the United States. Now, the other guy who was involved, as were others, in the development of liquid-cooled inline engines was this man, Glenn Curtiss. Now, Glenn Curtiss had been into the combustion or the internal combustion engine for a long time. Way back in 1902, he was designing engines for motorcycles. In 1907, he got that first V8 motorcycle engine. And you can imagine what a V8 motorcycle engine was slung underneath the frame of a motorbike. And he created a record which stood for many, many years here in terms of speed record for motorcycles. In 1915, he developed the famous OX5 V8 water-cooled engine, and probably the best-known application of that was in the JN4 Curtiss Jenny during World War I. And in 1915, he also came across a guy called Charles Kirkham, and he pulled him into the Curtiss operation here as the chief motor engineer, as the title there indicates. And Charles Kirkham understood the ideas that Curtiss had himself about developing an effective water-cooled V12 engine. And the only problem of the engine that Curtiss and Kirkham put together themselves was that it was a 400 horsepower V8 engine. And of course, it had to make an inroad into the marketplace in spite of the Liberty engine, which was already adopted by the United States government as kind of the standard power plant that would be used for all applications in World War I. However, during the time that Kirkham was involved, and it was a short time, only a couple of years, with Curtiss, he developed the cast aluminum crankcase ability. He put in that casting integral cylinder blocks. He also recognized the value of 4 valves per engine, and he also made what's noted down there as wet sleeve. What that meant was that the water cooling was in direct contact with the steel liner that was in the cylinder for more effective cooling. And he developed this engine here, the K12, 400 horsepower nominally, and it became, after a few years, the C12, adopted by Curtiss, because Kirkham left the Curtiss company and went off to set up his own company. And we shall see a little more of that a little later on. But Kirkham, while he was still working on the C12, had some propeller, it started working the science of propeller reduction gear, recognizing the engine ran at an RPM that was more efficient than a propeller operated because of the limits of the tip speed of a prop. And so he developed some propeller reduction gears, but he had problems with them earlier on. And Curtiss, after Kirkham left the company, Curtiss went to a version of this V12 engine called the CD12, which was a direct drive version of the C-12 engine. Further development of the engine and refinement went on to a final version of this engine, which was called the D-12. And this was where Curtiss, not being able to get involved in the kind of standard competition with the other 400 horsepower Liberty engine, he concentrated on focusing his attention on the racing circuits, both on land and in sea, as we'll see in a minute. And he also started working with the military to overcome the competition with the Liberty engine, to apply his engines to military fighters, and we'll see that with the next chart in a minute. It's just a cross-section fore and after of the D-12 engine. Right at the beginning of the 1920s, we see an example here where Glenn Curtiss got together with a Texas millionaire, a man called Sam Cox. And Curtiss started not only to experiment with engines, but he also experimented with airplanes. And for the 1920 Gordon Bennett race and for several of the other race applications, including Pulitzer, Curtiss started experimenting with the airplane as well as the engine. And what we see here is a couple of those versions that Sam called the Texas Wildcat and the Cactus Kitten, where the first one at the top there was a monoplane, high-wing monoplane, closed cockpit, and those squares and oblongs you see on the side are actually the heat exchangers for, or the radiator for cooling the liquid from the D-12 engine that was up front, or the C-12, I should say. On the 1920 Bennett race, he had this airplane is a biplane. And then ultimately, for the 1921 Pulitzer race, he had an open cockpit triplane here. And that was the one that really took his fancy in the end. But Curtiss was really beginning to feel his feet here in terms of getting involved with not only the racing, but also to look at not only land airplanes, but also seaplanes, that we'll see in a second. In the 1920, one of the races that was involved, as well as the Gordon Bennett race, was the race by the newspaper owner, Pulitzer. And he got Curtiss to put together his CR-1 airplane, which you see here in the left for the 1921. The airplane was borrowed from the Navy, although it was pulled back and just used by Curtiss, borrowed from the Navy, and it was his chief test pilot, Bert Acosta, who flew that airplane and won the 1921 Pulitzer race. Now, 1922, Verville was still active. In this case, they used a smaller monoplane that you see at the top of this picture here for the 1922 race. And they had it used a V8 Wright engine for power plant on this, so it was a much smaller airplane. But that won the 1922 race. It was really developed, it says developed by McCook Field, which is really the early days of Wright-Patterson. And a lot of very prominent engineers in the engine and airplane business were working out of McCook Field in the beginning of the 20s. Curtiss, however, pressed on with his ideas about biplanes, triplanes, and this kind of thing, and pulled together the 1923 Pulitzer race here with the Curtiss 221. And it was an Army lieutenant there, Ashford Williams, who won that race. And I said Army, I meant Navy. And it was at this point that Curtiss spread his wings even further, putting floats on this particular airplane and using it for the American entry into the 1923 Schneider Trophy race, which was won by that airplane. It went on as a development 2 years later to be the airplane that Jimmy Doolittle won the 1925 race with Schneider Trophy race. So you see here, Curtiss is really spreading his wings in terms of, in more ways than one, in this whole business. And those airplanes there, let me just go back here. The Bert Acosta's airplane here and the Verville airplane up there used an advance of coolers called the Lamblin radiators, and these were colloquially known as the lobster pots, developed by the French in 1918. These circular coolers were slung under the airplane, as you see here, and inside they had annular tubes that carried the coolant and plates on those annular tubes that supplied air cooling for that coolant. And this was reputed to have added 15 odd miles an hour to some of the first airplanes they tried to use. And it was used as a development to improve airplane performance and engine performance. And it was just a precursor really to this idea, which was Curtiss's designed surface radiator that he used for the Schneider Trophy races, as well as that Williams racing airplane I just showed you. These are really brass tubes that are carrying coolant that are really the kind of, I suppose, the grandfather of the plate fin coolers that we used many years later. The same kind of idea was being developed at Supermarine with R.J. Mitchell, and he was putting these kind of coolers right down the side of the fuselage of the Schneider Trophy airplanes in 29 and 31, whereas Curtiss here was using them as a wing surface, both of which were very effective as coolers. And here we see kind of the ultimate development of the Curtiss designed engine. This is the Conqueror, and the Conqueror was developed right at the 1932 or thereabouts, and it serves to show that Curtiss had further ideas about developing these. It was the first engine to power an airplane to go over 200 miles an hour. He started to think about pressurizing the water cooling system in these engines. And by pressurizing, of course, he can raise the boiling point of the coolant. He started to mix it with glycol, ethylene glycol. Now, for anybody who's used ethylene glycol in an engine, you'll know that glycol will find a leak if there is one. And using 100% ethylene glycol really was a bit of a disaster all over the engine business. But using a 50-50 system, he could get the cooling system to operate to a boiling point of 300 degrees Fahrenheit, which was significant. And he also used another idea in this engine. If you look at the reduction gear for the propeller, which is on the right side of that engine, let's see if I can use the pointer, you see a double set of helical gears here. Now, initially in the engine business, guys used spur gears because they were easy to machine, and they were also noisy, and they had a contact line here, which was not very efficient in terms of transmitting mechanical power. If they used a bevel gear, which is what you see here, or what you see here is a gear where the teeth are angled, helical gear, if you like, which were much quieter and more efficient. The only problem with that was that being at an angle, you needed to support that gear with a thrust bearing because it exerted an axial force when it was operating. And what Curtiss tried in this engine was a split gear here, one facing one way and one facing the other, and you get away with using that gear without a requirement for a deep groove ball bearing to take the thrust loads. You could get away with roller bearings, and that was a lot lighter and a lot easier to maintain, a lot easier to produce. This engine was supercharged also, and it had it was about a 600 horsepower engine. Was the ultimate, well, it was more than 600 horsepower, and it powered this airplane here. Finally, Curtiss broke through with the military, and this engine here, the Curtiss Hawk Fighter, was initially supplied with a V1400, which was a 500 horsepower version of the Curtiss engine. Remember, originally, his engine here was the C12, the C12 was producing 400 horsepower. The V1400 capacity, 1400 cubic inch, excuse me, was gave about 500 horsepower, and then the Conqueror, which was a 1570 cubic inch engine, that supplied 600 horsepower. So 4, 5, and 6 was all tried on the P1 Hawk. They replaced it with a C12, or they replaced the V1400, which had problems, both in the gearing and in the engine itself. They superseded it with a C12, and it be a supercharged C12, and it became a P2. Then they replaced the engine with a basic D1200 or D12 with a geared prop. And finally, they fitted the 600 plus horsepower Conqueror, and that became the P6 version of this Hawk airplane. And it was used in the services from 1929, but it was pulled during the early 1930s or mid 1930s. And that engine kind of disappeared at that point. Excuse me, at least in service. I should mention here that after Kirkham left Curtiss, the man who picked up the development work was this man, Arthur Nutt. And Arthur Nutt was involved in the development of CD12, the D12 itself, the V1400, and finally the Conqueror, the 1454 engine. And he became, after the Curtiss Wright Corporation was formed, and I'll tell you that in the next slide, but he became Vice President of Engineering for the next 14 years, and was also a director of the Packard Company from 44 to 49, and then went on to produce his own company in 49 to 51. I guess you could argue he couldn't hold the job down, but he did a tremendous job in every company that he worked for throughout his career. Now let's talk about the Wright Company for a minute, because I find that there's quite a bit of confusion usually about the Wright Company and how it developed. This chart attempts to summarize that. Excuse me a moment. Thank you. The original company, of course, was formed by the Wright brothers back in 1903. In 1916, it merged with the Glenn Martin Company, excuse me, and they had a license to build Hispano-Suiza V8 liquid-cooled engines for the services. In 1919, at the end of the war, Martin backed out of that, and the company became known as Wright Aeronautical Corporation. And in 1923, a man called Charles Lawrence, who we'll see in a minute, Charles Lawrence developed an air-cooled radial engine. And Wright Aeronautical had some real ambitions to get into the air-cooled radial engine, particularly since the Navy was averse to the liquid-cooled engine because of its complexity and its probably compromised ability to be maintained at sea on a naval application. So Lawrence produced an engine for 200 horsepower back in early 1921. And the Navy got very interested and said, we'd like to buy about 200 of those things. But the naval brass decided that they were confident in Charles Lawrence's technical ability, but they weren't quite so confident in his ability to produce a couple hundred engines that the Navy had ordered from him. And so they went along to Wright Aeronautical and they said, they got a hold of the president of Wright Aeronautical, Fred Rentschler, who we'll see a lot more of in a few minutes. And they said to Fred, we'd like you to take over the Lawrence Aero Engine Company. And Fred had his own ideas about developing air-cooled radials. And he said, no, I'm not so sure about that. And the Navy came along and said, Fred, put in low fog index language, if you'd like more naval orders for your license-built Hispano-Suiza engines, you will take on Lawrence. And at that point, Fred Rentschler said, okay, that's the reality of the world. And he signed on Charles Lawrence, who came along as a vice president of the Wright Aeronautical Company. And as we'll see in 1923, 1924, I beg your pardon, Fred Rentschler took his ideas for his own air-cooled radials and resigned as president of Wright Aeronautical at the end of 25 and at the beginning 24, and at the end of 1925, he founded Pratt & Whitney, and we'll talk about that in a few minutes. In 1929, Wright Aeronautical, and of course involving Lawrence as well, merged with Curtiss, and that was the origin of Curtiss-Wright Corporation. So that's kind of the development of Curtiss-Wright. And it's, of course, their air-cooled radials that we'll hear a lot more about as we move through the 30s and into the 40s. And they were, of course, in competition with Fred Rentschler at Pratt & Whitney, but we'll work that in a moment. Fred Rentschler, although he had his own ideas about air-cooled radials, he had a kind of jaundiced view of his board of directors at Wright Aeronautical. Many of them were, in fact, all of them were non-aeronautical types, non-engineering folks. They were mainly finance guys. And Fred considered that they weren't adept enough at getting air-cooled radial engines to the right place in the market. And in the end of 1924, he resigned. And he took with him the chief engineer of Wright Aeronautical, excuse me, Fred Meade, or George Meade, the man on the right of this picture. And he also took George Meade's immediate deputy, Andy Wilgoose, and a couple of other people that he took in there as well. So he basically gutted Wright Aeronautical Engineering to form Pratt & Whitney. He went on to take over or buy a small, failing really tool company in East Hartford called Pratt & Whitney, and formed Pratt & Whitney Aircraft in 1925. And the ideas that he had on air-cooled radials, and those ideas were shared in depth by George Meade and Andy Wilgoose. And they produced this engine, the 1340 cubic inch Wasp engine. Fred Rentschler had told his staff, which was fairly small, and by the way, they started designing this engine in Andy Wilgoose's garage. You know, we think all of our modern inventions are started out in garages, a lot of the software business, and computer business starts out in garages. Well, this engine was one of the first to start out in a garage. And Fred Rentschler told his staff, he said, if you can get an engine on test before Christmas 1925, I'll buy Christmas dinner for everybody's family. And that is exactly what happened. 2 days before Christmas, 1925, this engine ran for the first time. And it was quite quickly absorbed in terms of its ability. It met its performance guarantees very early on. It was a 400 horsepower engine. And it was ordered by the Navy in October of 26 for 200 engines. Now, historically, by 1960, they built 39,000 of these engines, which gives you an idea of how Fred Rentschler applied his thinking about air-cooled radials. So we see an advance in Wright engines that we'll talk about in a second, and we also see advances in Pratt & Whitney engines. It was quite obvious right from the off that the marketplace for the Wasp engine, which was, the Wasp engine was initially in 1927 put into the first versions of the Boeing Model 40, which entered airline service, where the Liberty engine, being liquid cooled, was abandoned by Bill Boeing, who knew Fred Rentschler, and they both became co-directors of United Technologies. But Bill Boeing had been persuaded to use this engine as a much lighter version, and it basically doubled the payload that the Boeing Model 40 could carry. So it was a very smart move. But it was obvious right off the bat that instead of a 400 plus horsepower engine, a smaller engine was needed, and this engine was developed. It was a scaled down version of the Wasp, and in 1930 became known on the marketplace as a 985 cubic inch engine as the Wasp Junior. Nominally 300 horsepower, but again, for a point designed airplane, it could be boosted considerably. And Matty Laird used it in the first 1930 Thompson Trophy race around the pylons when it was rated at 470. Now, Matty Laird used that, but the race itself was won by a man called Speed Holman, who was famous on the racing circuit here, using an airplane known as the New Solution, which was a travel air airplane. Holman himself was killed a couple of years later because he flew everything. He came across his nickname of Speed Holman quite honestly, and he was involved in some very, very fast, low-level airplanes that were doing some violent maneuvers low down in the Thompson races. And it was this engine, or this airplane rather, that became Speed Holman's demise in the end. The engine X kept on being boosted, really made 500 plus horsepower in 1931, and it was Jimmy Doolittle who made this engine somewhat famous by mastering it in his GBZ engine or airplane. I got almost said his GBZ engine there, because that airplane looks like an engine that's allowed a very minimal sized airframe to fly as a speed airplane. But Jimmy Doolittle was one of the guys who could really handle that airplane with those kind of horsepower levels. But that's another story. What happened at Wright? Well, in 1921, Wright Aeronautical had taken this man on, Sam Heron. Sam was a Brit engineer who'd worked at the RAE at Farnborough in Britain, and he'd worked with a man called Professor Gibson, and the pair of them had spent a very great deal of time and effort trying to understand air cooling, and particularly the science that's involved in exhaust valves, which again, I think it was Stanley Hooker at Rolls-Royce who said that some engines were specifically designed as destruction mechanisms for exhaust valves. And it was Sam Heron who came across the idea of lining an exhaust valve, which he patented, with sodium. And he tried various metals, but the idea was that you use the latent heat that was required to change a solid into a liquid as a cooling mechanism within inside a valve. And it was Sam Heron who exercised that to begin with, really advanced the technology considerably, and you see a few of his exhaust valve ideas there on the top right. He also got involved with trying to increase the compression ratio of engines by becoming interested in the science of tetraethyl lead, which we'll again talk about in a minute, that opened the door to high octane fuels that could take higher pressures than the nominal 6-to-1 compression ratio that most engines had in those days. And he became a director of research at the Ethyl Corporation, which was the corporation put together to create and to produce and market tetraethyl lead for increasing the octane number of fuel. Here's a cross-section of the Heron-Gibson, Professor Gibson, back at the RE at Farnborough. And this was when Sam Heron was playing around with mercury-fueled exhaust valves this time. They found sodium was a better one, but he was doing a lot of research with Gibson on the shape and size and location of air-cooled fins on the engines, cylinder barrels likewise, how to put steel liners inside the cylinder head by screwing them in instead of shrinking them in many cases. And he was working on the valve shapes and the valve guides to keep these things as efficient as possible. And the first engine that was produced from the marriage of Charles Lawrence and Wright Aeronautical was an engine called the J1, which was a 200 horsepower 9-cylinder engine. And it was George Meade and Fred Rentschler who did some of the development work along with Sam Heron on the J1 and J2 engines. But then, of course, Fred Rentschler and George Meade left Wright, and it was then left to Sam Heron, George Nutt, and further people there to develop this series of engines. And over several years, this engine became known as the Whirlwind, and it developed as a 9-cylinder air-cooled radial in direct competition with Pratt & Whitney. And by the time it got to the J5 version, that was the engine that was used by Charles Lindbergh in the Spirit of St. Louis to fly across the Atlantic in 1927. The publicity that was attendant upon that record and that flight made this engine very popular in terms of the racing fraternity. And as a 7-cylinder engine, let's just flip it over here to the next development, really. A travel air airplane known as the Mystery Ship for the 1929 Thompson Cup is seen there on the left. That had a 9-cylinder, 975 cubic inch engine at 400 horsepower, which won that particular race. And the famous Pancho Barnes also used a 7-cylinder version of that engine as a 225 horsepower that you see here in an entry that she made in the various races that were available to her at that time. You see her with her hands there in the bottom right picture, holding on to what became known originally as a town end ring. And really what it was a cowling around the air-cooled cylinders, which speeded up the air that was coming into that inlet to improve the heat transfer from the aluminum fins to the air that went through that town end ring. So it just improved that. NHCA's got a hold of the same idea and developed it further and produced the full cowling that you see there on the left, 1929 Thompson Cup winner, which was a bigger cowling, which also not only improved significantly the airflow past the air cooling engine, but it also gave the ability on later engines that applied that technology to use radio or shutters, if you like, and doors in this gap back here to open up allow a lot of cooling air to flow through the inside of the cowl for takeoff and high power operation of the engine. And then at cruise, where you didn't need so much cooling, you can close it off and get rid of the drag effect of those cooling doors. But there we go. That full cowling was used first of all in the 1929 race that you see there. Okay, let's talk about some of the other things that happened here with the advance that took place in 1929 beyond what we've seen so far. Pretty well all the engines we've talked about so far, and the same operated in Europe as it did in the United States, about 6-to-1 compression ratio, because beyond that, you ran into a problem called knocking or pinking. Now, let's just talk about that for a minute. As I said earlier on, the gasoline fuel needed to be vaporized with air in order to give efficient combustion. And in the engine itself, the separation between the burning gases and the unburned fuel-air mixture is called the flame front. And that moves through a cylinder as the air-fuel mixture is resident within the cylinder. Now, after the spark plug initiates combustion, the air-fuel mixture ahead of the flame front is compressed, because obviously the burning gases are expanding. So they're compressing the unburned mixture ahead of the flame front. And it can get to the point where that fuel-air mixture diesels. In other words, it spontaneously ignites. And that is post-ignition knocking or pinking. And it was Charles Kettering, who you see on the left here, who was the vice president of research of General Motors, who taxed his staff, including a man here called Tom Midgley, with figuring out why it was that engines couldn't stand a pressure ratio higher than about 6-to-1 at sea level before it ran into pinking. What Tom Midgley and Charles Kettering found out was that if they could add a heavy metal element to the mixture of fuel, that they could improve the knocking capability of the engine. And this they did a lot of experimental work on. And a man called Harry Ricardo worked with them in depth in Britain to develop this kind of technology. And then several other people got involved in that as we went through. But this came up with this additive for straight gasoline fuel called tetraethyl lead. And they decided to call it ethyl because it got away from the lead. Lead, of course, was recognized as something which was a poisonous metal that could lead to health problems that were ignored by Tom Midgley, who famously washed his hands in tetraethyl lead, and he died at a very early age of lead poisoning. But we won't go into that one in depth. However, the ability of adding tetraethyl lead to fuel, gasoline fuel, meant that we came up with what we know as leaded fuel, and the measurement of the ability to withstand higher pressure was developed both in the US and in Britain with Ricardo. And Ricardo actually built an engine in Britain that was a variable compression engine that would give you what became known as the octane number, which was a measure of the ability to withstand higher pressures. What this did was open the door to supercharging. And this man right here, Sanford Moss, excuse me, had graduated from college way back at the beginning of the century. And he had joined General Electric's steam turbine division. And it was Moss who developed the impeller that you see on the picture here. Excuse me again. And applied that to improving the pressure of the air that you mixed with fuel, and allowed, therefore, at altitude in an engine, more mass flow of air to go through the engine, and therefore more fuel. So that just took that charge weight of air and fuel that we mentioned way earlier on in developing power to increase significantly as you increase the pressure of the air that was involved with the fuel. And it was Moss who ultimately developed the exhaust supercharger that also recognized all that waste heat that goes out through the exhaust pipe, and famously developed the exhaust supercharger in later years for all the applications within military airplanes during World War II. But that again is another story. Moss developed this supercharger or rotary compressor, if you like, and applied it on a French airplane that had a Liberty engine. And he did that back for part of the National Air Races, which involved airplanes powered by Liberty engines. And in 1922, the man on the left there, Lieutenant Koenig, won the Liberty engine section of that National Air Race with this French airplane, the La Perle-Lussac, which you see up there with a big impeller casing on the front of the engine. We'll look at it in a second. One other thing that did happen with that combination of airplane engine was that Lieutenant Macready, who you see on the right there, had proved the point about supercharging engines by allowing that airplane to fly to almost 41,000 feet. And you see him there suitably dolled up in not a pressure suit, but a suitable dress for getting to that kind of altitude short term. Here's the engine itself. That's a Liberty engine. And you see the impeller casing up front with the exhaust of that disappearing off into a carburetor that then pushed into the cylinders of the Liberty engine in between the V's. And then you see the exhaust manifold on the outside that takes the exhaust manifold aft for exhaust there. And the cooling radiator you see way up the top there, a big flat thing. But nevertheless, it worked. Fixed pitch propeller, of course. And it was at this time that you saw the power increase. And this is where, if you remember back on those trend charts we had initially, in 1929, the air-cooled radial engine took off in terms of power capability. And that was where the run-up to World War II had that total development of high-powered air-cooled engines, all due to, first of all, the introduction of the high-octane fuel, but then also to this introduction, which was the variable speed or the variable pitch propeller. And it was developed in various places concurrently, really. The initial patent for a constant speed propeller, which was one that allowed the engine to run at a constant speed, whereas the speed of the propeller, the speed of the propeller was constant, but it changed pitch as the power changed, or the power requirement changed as you got to higher and lower altitudes. And that was developed in Britain by these two guys up here, Healy, Shaw, and Beecham. And then below, you see a Grumman FF-1 fighter that was the first production airplane in the United States Navy to operate with a constant speed propeller. Just coincidentally, later on in the 20s, 1929, Hamilton Aero, as it was known then, merged with Standard Steel Company, and that created Hamilton Standard, who became really the #1 United States producer of variable pitch propellers. We see here Wallace Turnbull. He was an inventor, an engineer in Canada, who developed the first variable pitch prop. They hadn't quite got to the point of constant speed at that point, but he put a constant pitch propeller on a rotary engined Avro 504 back in the early days. And he operated that engine in 1927 to demonstrate that capability. He also then sold all of the patents that went with that to a part of the Curtiss company later on in 1929. The man who really developed the technology here at Hamilton Standard was this man, Frank Caldwell. And Caldwell developed the controllable pitch prop, as it said, and he developed the hydromechanically for two of the first two airliners down here, the Boeing 247 and the DC-2. That's what Hamilton Standard called gear shift in the air, really, that was used by some of the racing pilots to improve, obviously, the performance during the racing process, too. So here we see how some of those racing engines from the Wright company and from the Pratt & Whitney company serviced the airplanes that we've used during World War II and in the commercial market also at all levels. So you see the basic WASP that was used in the 247 and along with those improvements in the compressor, or the propeller technology, the DH Canada Otter and the Texan, the T6. And you see a lot of famous airplanes all the way through that list that we use not only in World War II that now operate during part of museum collections, but you also see airplanes that, or engines that are still around for many of the airplanes that we see in museums today. And several of those airplanes you will see with those engines in the Historic Flight Foundation collection. Likewise here, if you look at the Cyclone versions or the Wright engines that were developed, the 9-cylinder single-row B-17 engine, then the 14-cylinder twin Cyclone, used in the 314 Boeing Flying Boat, the big Avenger that you will see in the Historic Flight Foundation collection, the B-25 Mitchell likewise, and then the A-20 Havoc. And look down there at the biggie there, the 3350 18-cylinder Cyclone engine, and that was used in the B-29. The Skyraider that you will see from in the air races around here, flown by the Skagit stable of airplanes. The Neptune, known by many, many people who flew marine flying back in the early days of the piston engine maritime reconnaissance airplanes. And just a small postscript to this. In 2016, just before we actually produced this story originally, in 2017, ASME designated the R1340 WASP engine as a historical engineering landmark, or absolutely establishing its position as a landmark in technical excellence and technical significance, both in engineering and aviation. And that, I'm afraid, kind of ends this part of the story. And I want to thank you for your interest and for your attention on this one, and bid you goodbye at this point. Thanks a lot.